right, the next talk is on my own research on concrete construction on Mars. I'm going to shorten it a little bit to keep on schedule. I did my initial the biggest problem we have, of course, is the cost of transporting material to Mars, so any construction is going to have to be done with materials found on site, in situ resource utilization, and it has to be done as soon as possible. One thing we do have on Mars is sand and gravel, which are the main components of concrete. So the simple solution there is to take a concrete plant to Mars to build concrete. Now with Portland cement, the biggest problem we have is water is one component, and it has to remain liquid in the concrete during the curing process, which can take several weeks. If we tried to use that on Mars, the water would evaporate before the concrete even has a chance to set. There's another type of cement called magnesium oxychloride cement. It's composed of magnesium oxide, magnesium chloride, and water. Now, since the water is mixed in with magnesium chloride, a salt, in a very dense brine, it can remain in liquid form without boiling in the Martian atmosphere, which has a pressure of less than 1% of Earth's atmospheric pressure. And it cures very quickly, within a day, so it can cure before a significant amount of water evaporates. It's also much stronger than Portland cement, but it has poor water resistance, which is why we don't use it for structural applications on Earth. Since we don't have a lot of liquid water on Mars, little if any, that's not a problem. It also requires less energy to produce than producing Portland cement, and we have found the raw materials for it on Mars, specifically magnesium carbonate being the main component, as well as magnesium chloride and, of course, water. As I said, the advantages is very strong, fast curing, and easy to produce. Now, for my, what I did was just a feasibility study to prove that it can be used on Mars in the same way you use concrete here on Earth. So the concrete mix that I came up with, I based it on a mix for a low slump Portland cement concrete like we'd use here on Earth. Here's an example of it. It's just a ball. I formed it by hand into a ball and set it down so you can see that it holds its shape. That's what I mean by low slump concrete. You can slap the side of a form, compact it there, and let it cure. Let me pass this around so you can see. And to give you an idea of the strength, I bounced it on a concrete slab like a rubber ball, and it didn't even crack it. And since it is a different type of cement, there was a lot of trial and error in coming up with the mix. These are some examples that had too little and too much cement in there. You can see the porosity there. So this is the mix design that I came up with for my testing. And strength after 3 days of curing, I believe. No, actually, I believe this was after 24 hours of curing. 8,853 psi. Conventional concrete that we normally use here on Earth, it is rated around 5,000 psi, or 60. I also did flexural strength tests. I came out to 1,070 psi. And well, Portland cement concrete would generally crack all the way through. Once it starts to crack, that crack would propagate all the way through. When this did fail, the crack only went about halfway through the beam. You can see an example of one of the flexural test beams. That was after it was tested. The crack went about halfway through. And if you can see, here's the crack that where it failed, and this is an example of my direct tensile test for concrete that I came up with. And my initial batches came out with an average of 954 pounds per square inch tensile strength. After a longer curing time, I was able to get over 1,000 psi, around 7 megapascals of tensile. And this is a picture of my test rig that I had to build myself. Inside here, that's the vacuum chamber I used for the testing. It's just a simple 12-inch vacuum chamber. I tested it around 7 millibars, which is around average atmospheric pressure on Mars. And these are the samples themselves. They're in test 4-inch diameter cylinders with the tops open, so it was open to that atmosphere. Now, the problem I had was I wasn't able to vibrate the samples to get the dissolved air out of the mix, so I had a bunch of air bubbles. In use, the concrete would be subject to heavy vibration to force those air bubbles out of the mix to get a solid, so it sets up solid without those bubbles. So I had to, those were the samples I had. When I came out with the void volume from those samples was about 17%. I also, by weighing it before and after, found out I had lost about 9% of the water to evaporation, which was still enough to allow for a full cure. Now the final strength I had out of one batch, I made three samples at Martian atmospheric pressure and 3 samples at ambient pressure outside of the chamber. Trial sample 554 psi. The controls 6,382 psi. This was during a shorter curing time. That's why the strengths are lower than the previous tests. To account for that, this is what you see here is an example of some testing of compressive strength as a function of void volume. The line that's relevant here is the compressive strength line. And at 17.3% void volume from this sample, which is for Portland cement concrete, at 4,800 psi with 0 void volume, we would expect 2,200 psi at 17.3% air content. So 1,934 psi. Our actual trial strength is 87% of that, pretty close. And since this is a rough estimate, that's about what we would expect. And now for the main component is magnesium oxide, which can be produced by heating a naturally occurring mineral. We have multiple possible sources. Magnesium hydroxide, called brucite. The most common would be magnesium carbonate, which we have found on Mars. Another possibility is magnesium sulfate, which we've also found to be plentiful on Mars, but it requires about twice as much energy at much higher temperatures. So that would be used as a last resort. And the magnesium chloride, we extract it from seawater and brine deposits here on Earth. We should be able to find similar sources on Mars. We have found salt deposits on Mars, and there should be a significant amount of magnesium chloride. And the magnesium sulfate is a minor additive used to improve durability and chemical resistance, and that's been found to be plentiful on Mars. And of course, the third component is water, which we also have found on Mars. This is an approximate energy budget for producing it. Now, from a rough estimate, if we had, based on the type of power supply, if we had a nuclear reactor, 20 kilowatt continuous electric be enough to produce the kind of amounts we would need. And if we're dealing with solar power, assuming 5 effective full power hours per day, borrowed term from the nuclear industry, we would get away with 100 kilowatts of rated power to supply our cement production. And these are some estimates for earth moving capacity required, ore transport, and precipitation tanks if that